We have a couple more things to talk about in section 1.2, and I'm just going to give you the numbers I used last time just to remind you what they were. These were, we had numbers 5, 8, 12, and a bunch of 13s, 4 of them in fact. And then 14, 16, 17, 18, 19. And we talked last time about the idea of Q1 and Q3, but our next topic, our next kind of number you can calculate for these, I believe it's the 8th thing we're going to talk about, is something called IQR. And IQR stands for interquartile range. So let's begin by thinking about there's 12 numbers here, right? Let's make sure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. So let's figure out the median would be the average of the middle two numbers. So the median is the average of these two numbers, right? 1, 2, 3, 4, 5. No, sorry. The average of these two numbers, which doesn't really matter. The median is 13. So then Q1 is all of the median of the first 6 numbers, and Q3 would be the median of the last 3 numbers. Now there's 6 numbers here, so Q1 has to be the average of these 2 numbers, so Q1 is going to be 12.5. Q3 is going to be the average of these 2 numbers, which is 16.5. So the formula for IQR, pretty straightforward, is just Q3 minus Q1, which in this case would be 16.5 minus 12.5, which is 4. So we would say the IQR here is 4. Now, so what does that tell us? Well, think about if Q1 is the 25th percentile and Q3 is the 75th percentile, aren't 50% of things between Q3 and Q1? So the middle 50% are in the range of the middle 50% is 4. That's what that kind of tells us. Okay? Moving on a little bit, next kind of important idea, and that is the idea of something called, number 9 I'm going to call this, standard deviation. Big idea in statistics. You're going to see this over and over and over again. And standard deviation, the symbol we use for it is S. And what does standard deviation mean? It means the average distance from the mean. Now what does that mean? We calculated before that the mean of these numbers was 13.42. Well, think about our first number was 5. Well, how far away is 5 from 13.42? Well, its distance is, 8.42, right? Our next number is 8. Well, how far away is that from 13.42? What's our distance? Well, it's 5.42. So see, for each number, 13, for example, is how far away from 13.42? Well, just 0.42. If you did that for every single number and then averaged all of the distances, you would get the standard deviation. So it's the average distance away it is from the mean. And notice I'm using distance because it doesn't matter. I'm using this kind of funky notation. How far away is 19 from 13.42? Well, it's 5.58, right? So it's a distance, which all these numbers, when you think about distance, would have to be positive. The good news, almost never are you going to calculate standard deviation by hand. Usually your calculator will just do it for you. And I'll show you how to do it in class, but the standard deviation of these numbers ends up being, the calculator tells us 3.988, let's say, okay? Which means on average the numbers are about 4 away from 13.42. That's standard deviation. Standard deviation is very much related to something called S squared, which is just standard deviation squared, but it's kind of important, so we give it a name. It's called variance. So variance is nothing more than standard deviation squared. Now, we don't really care about variance very much, although it kind of tells us that it's how much things vary. But the only really reason that I eventually use for standard deviation, it's easier to write the formula in terms of variance. Let me kind of give you that formula. So here's our formula for variance. Okay, it's going to involve this big sigma, and then how far away is each number from thing? Well, x is an observation minus x bar. X bar, remember, is mean. Okay, we're going to square it to kind of match up the squareds. And then the one goofy thing is we end up dividing, you'd think it'd be divided by n, but actually it's actually not. It's divided by n minus 1. Now why is that? For right now, don't worry about it a ton, but you think about it, if n is really, if you have hundreds of numbers, it's not going to matter really too much. Okay, but it's kind of lost. We'll talk about that a little bit later on. You kind of just have to remember you're really not dividing by the number of things, you're dividing by one less than it. Which really gives us the formula for standard deviation is the square root of all that, right? X minus x bar squared over n minus 1. Okay? But again, the calculator will almost always do it for you. And a couple notes about standard deviation. Standard deviation is always positive because it's always a distance. Okay? A big standard deviation means what? It means your data is really spread out. Data is really spread out, not the most mathematical term. And the last thing is if s equals 0, well, that's the only way that could happen, would mean all the numbers are the same. It's the only way s could ever be 0. Okay? So that's all the kind of calculations we're going to do in this section we about next. And these are just a few ideas related to the numbers we've been talking about in section 1.2. And the first idea is something called resistance. Resistant versus non-resistant. And the term resistant really means resistant to change. To change. And the easiest way to think about this is consider those numbers I gave you and imagine what would happen if you added one really, really big number, or the last number was 19, change that 19 to 100, right? Suddenly there's a class of 100 people. Would the other numbers change a lot, or would they change kind of a little? And we can kind of think about that a little bit. Resistant means it wouldn't change much, whereas non-resistant means it would change. So let's kind of just, I'm not going to do it for all of them, but let's kind of make a little chart of which of those numbers we've just done are resistant and non-resistant. Well, if you change the last number to a million, would the mean change? It very much would. So the mean is non-resistant. Would the median change? Actually not if you think about it, because if you make the biggest number much bigger, it doesn't really matter what's happening in the middle. The middle number is still the middle number. So the median, we would say the median is resistant, the mean is non-resistant. Okay? How about things like the standard deviation? Standard deviation, if you add a really, really huge number, suddenly the numbers get more spread out, so therefore that's non-resistant. Whereas something like IQR, if you make a big number, it doesn't really matter. So IQR is resistant. You can kind of go through and kind of the things I gave you, think about which of those things are resistant, which of those things are non-resistant. Okay? And we'll talk about that idea a little bit more in class. Next related idea